I think showing the public how effective the pollution controls have been in reducing acid deposition is a good step towards convincing them and policymakers that regulatory controls related to climate change can make a difference, and it's not all a lost cause. People sometimes get overwhelmed by these huge environmental issues, but I think we can make a difference, and we have made a difference, and I'd like to continue to do so.
Wow. Yeah, that's awesome. Oh my God.
Standing at 4,865 feet tall, Whiteface Mountain is known by many for its skiing and hiking attractions. However, this mountain is also the site of an abundance of scientific research.
Yeah.
Okay guys, it looks like we may be hiking up.
This group begins their journey to the summit, where the Whiteface Atmospheric Sciences Research Center is hard at work to collect data. Close to the summit, there's a short rest stop containing some information on the history of Whiteface and exhibiting some basic data collected on the mountain. However, the scientific research goes much further than what is seen at first glance. Even further along this path is the research center itself. The Whiteface Atmospheric Sciences Research Center records a vast amount of chemical data in order to predict atmospheric trends. Paul Casson, one of the few who maintains the facility, provides a bit of background as to the workings of the station's research.
I've worked doing cloud collection here since 1994 at the summit of Whiteface, and I've worked for the U.S. Forest Service for a few years. I've worked for the Adirondack Lake Survey Corporation for 13 years, doing acid deposition monitoring all over the park. I was the lead helicopter guy. We would do helicopter sampling monthly, lots of hiking, paddling, skiing, stuff like that. I'm a ski patroller at Whiteface as well, so I have a medical background. I just love the mountain. I have a real passion for the mountain and promoting it, and that's why I like to do tours like this. The first thing every morning I do is I measure whatever rain fell in the last 24 hours, and I report it on the weather WX Coder site for the National Weather Service. And then there's a lot of different things. So I operate the NADP site. I operate 2 CastNet sites. In charge of maintaining 4 buildings, helping fix the elevator, radio equipment. There's 12 different government agencies up here with radio equipment. I help with the cloud water collection for DEC. I'm also the vice president of the Whiteface Mountain Visitors Bureau, so I help promote tourism here. It's kind of all interconnected. Mercury is a hot topic right now, so I'm kind of more involved with the wet deposition measurements here, the cloud water and the precipitation measurements. So a lot of people are interested in that data. Rich does the trace gas data, so that's a whole nother part of what we do. And we also have another site down at Pinnacle, New York, that ASRC operates. So it really depends on the organization. I think the general public is most interested in the meteorological data, things like wind speed, temperature, and precipitation. The scientific community is more interested maybe in the chemistry of the wet deposition chemistry, or also the trace gas measurements.
All right, so this is our flow rate. So it should be around 3 liters per minute. We have a rotometer here and a mass flow controller. So this is the data acquisition system. This is the modem, the power supply, the mass flow controller. There's a little filter in here to keep water out of the system. So this
is a new.
That's ice falling on the roof right now.
Oh, is it?
This antenna gets ice on it. So if I one way to make that happen before people come up here. That's why I didn't want them going up on the roof.
Right. Wow. That was very graphic.
There's a specific instrument for each environmental variable that needs to be accounted for. Each tool can measure data accurately within a small margin of error and must be regularly calibrated with both clean and specifically concentrated samples. Measurements of variables such as trace gas, ozone, carbon dioxide, sulfur dioxide, cloud composition, mercury, and more are all used to help understand certain occurrences in the environment.
So this was a secondary collector I did this year for Syracuse University. They were interested in mercury in cloud water. So in order to collect mercury in cloud water, you had to use, everything had to be Teflon lined. You had to use Teflon bottles because the mercury absorbs into the plastic and it can leach out later. This here is a black carbon analyzer. And Rich can explain this more to you down below. These numbers were over 1,000 a few weeks ago when it was really warm. But the carbon itself is on the filter paper. See those little dots, black dots? So that's the black carbon that is sucking in out of the atmosphere.
Halfway down the mountain, there is a mid-station which focuses on collecting different types of data than at the summit. Richard Brandt, science manager of the station, explains some of the goals and findings of this research facility.
And what we do here is we don't do much biology, but we actually measure the state of the atmosphere and precipitation in the atmosphere to look at the chemistry and physical properties that affect the ecosystems in our area. The two chemicals of concern are sulfur, and when burning fossil fuel, sulfur can get into the atmosphere, it oxidizes and becomes sulfur dioxide, which is a gas. And then nitrogen oxide and nitrogen dioxide are other gases that are emitted from making electricity, burning coal, for example, and also emitted from cars, although they've cleaned that up quite a bit in the last 20 years. And so one of the primary things we measure, they're called trace gases in our atmosphere. We've been measuring the sulfur dioxide since full time, since about 1995. And so this is a plot of these bars represent the middle 50% of the measurements that we make, and the little whiskers are for the outliers. And then this little bar here is the average, and you can see that from 1995, these light gray bars we couldn't measure through the whole season. And so the light gray bars we're learning how to make the measurement, but the dark gray bars are complete seasons, and you can see our sulfur dioxide has decreased more than 80% since 1995, and that's a huge success story. That's because of the Clean Air Act and amendments to the Clean Air Act in 1990, and it's evidence that science can show that there's problems like acid rain, which seriously damage the biology and the ecology in lakes, and they can pass laws, and that policy can be studied to see that if there is an improvement. The oxides of nitrogen are a little more complicated. They actually there's agricultural sources, automobiles are more of an issue, and so NO sort of is bumping along, but one important one, NOY, it actually peaked about 2005 and now it's gone down, and I can assure you that it's still improving through 2014. So that's important for you guys to know, that there's some huge success stories. It's much like getting the chlorine out of the stratosphere with the Montreal Protocol. People were worried about ozone in the upper atmosphere. Without ozone in the stratosphere, we would get much more ultraviolet radiation, which would be bad news for us. We get bad sunburns and more cancers, but it's even worse for the plants. They can't tolerate high levels of ultraviolet radiation. And so that was an international agreement. Pollution that caused that was related to refrigerants like Freon, and they have chlorine in them. The chlorine would get way up to the stratosphere and then damage the ozone. And so these are a couple of cases where the science leads the policy. Between 850,000 years ago up until the year 1800, so over the last almost a million years, the carbon dioxide oscillated between about 190 parts per million up to maybe 290. And since the Industrial Revolution, when we started burning fossil fuels, it's gone from 290, now we're up at 400, and there's real concern about 570 when we double the carbon dioxide. There's going to be very noticeable climate effects that are going to affect the human population as well as the whole biosphere. And so this is one of the biggest challenges that we're facing in terms of pollution, and the policy is slow, but it's actually coming into place, and it's very complicated. And but I'm hopeful that will be resolved. And I think some of these are stepping stones, tools that we can think about on smaller scale problems that we've resolved, and we can figure out how to do it internationally as well. So another thing that I was kind of curious about, this sulfur is the big success story. Where is it coming from? And so knowing the wind direction at the summit, where you've already been up to the summit, I made a plot here, and these are for 3 time periods: 1989 to 96, 97 to 2004, 2005 to 2010. These are called pollution roses. And what they show is the average amount of sulfur dioxide. So what normally would be the y-axis is over here, and it goes for each one of these little bars. And it depends on the wind direction as to how much sulfur dioxide we get. So west and southwest. And if you just look at the map, that leads you directly to coal-fired power plants in the Midwest. And so that was the source of the problem. And both the policy forced the coal-fired power plants to decrease the pollution by putting scrubbers on, but there's actually legal action. New York State Attorney General sued individual power plants in the state of Pennsylvania because they were actually cheating on the rules. And so that was proven, and then they had to put scrubbers on. And so you can see that now a little bit from the southwest, but it's much smaller amount, and it's and there's also a little bit of sources from the north and the east, and that's that little bit of remainder is likely due to burning diesel fuel, for example, and home heating oil. So we can see that the sulfur problem was coming from afar. This one is ozone, and this one is carbon monoxide. And the word we use for these sorts of plots are isotropic. They're the same in all directions. So this is pollution it's more local, and it's coming from all directions. and we're seeing a slight improvement in both of them. But those are challenges that we're working on now. And another really hot topic right now is mercury, and Paul might have mentioned up at the summit that we're doing some pilot projects to measure mercury. It's in very small amounts. These amounts are parts per billion. So if you take a billion particles or a billion gas molecules in the air, only a couple will be SO2, for example. If you talk about mercury, it's parts per trillion. And so it doesn't sound like it would be much of a problem. It's such a low level, but it turns out that biological systems accumulate mercury. So the plants and plankton in the water, as they take in molecules for their sustenance, the mercury doesn't leave, and so they concentrate it, and then the fish goes and eats, the herbivore fish goes and eats that plant, and it itself concentrates it. And as you go up the food chain, it can actually be 1,000,000 times more concentrated than it is in the air. And so that's why it's a concern for us, is the bioconcentration.
So this system is set up to do audits of all the NOx gases, NO, NOx, SO2, CO, ozone. And what we do is we have a dilution system, source of zero air, clean air, and we have pollutants in tanks. And we generate a concentration, a mixture of that gas, and send it to the site analyzers to challenge them with some known concentrations. We have a standard analyzer that we use to measure the concentrations that generated.
And does this site work out to be kind of like a base site for other locations because of its sort of rural in the woods nature?
You mean the location here?
Yeah.
Well, the networks have certain parameters they have to meet. Certainly, they have to be kind of isolated, not to use local sources of pollutants. So all of them are very similar.
Okay, I see. Very neat.
The Whiteface Mountain Field Station focuses on basic meteorology, along with particle sampling from gases and rain.
The pollution can come in many forms, or these gases and particles. It can be just gases like I'd mentioned, like ozone and sulfur dioxide, nitrogen oxide. It can actually come as little tiny particles, and we call those aerosols, not water drops as clouds or rain, but particles. And then it can also be mixed in with rainwater. And so one of the important things is to figure out what the sources are, is to collect these separately. So if you go in a lake and you measure the acidity in a lake, the question is, where is that actually coming from? You want to know, is it particles, is it from the rain, is it in the clouds, or is it gaseous? And so we measure all those things here. Set up for this. Okie doke. So what goes on in here, you need a dry space to do a lot of these gaseous measurements and certain particle measurements. And the other thing you need to do is to sample the air, and that sounds easy, but it's actually a little tricky. One thing, all of these particles that we consider pollutants are pretty reactive, and so if they touch particularly metals, they will change into something else, or they'll stick, and so that you won't actually be able to measure them. So on the roof we have a glass candy cane, if you will, and the air goes down this tube, and then if you look all the way at the end of this tube, there's a little fan at that end, and that's just constantly drawing what we call ambient air through this manifold. And then another thing that most of these pollutants or atmospheric constituents don't interact with is Teflon. So these are Teflon tubes that come off the manifold and go into the different instruments. And so we're measuring carbon monoxide, and right now that's there's an offset, so that's about 100 parts per billion, and that's pretty normal for this area. And for the Northeast, we rarely go over about 200 parts per billion, and so we're well within the safety limits for humans. And part of all of this monitoring is driven by the Federal Environmental Protection Agency to make sure that as humans we aren't exposed to high levels of pollution. And there are times in our country when, especially in certain cities like Los Angeles, when they do go out of compliance. The levels are so high that there's health risks, and they'll even tell people with compromised respiratory systems to stay inside. But the goal is to prevent that from happening in the first place. China is in the middle of dealing with this right now, and there's a very new awareness, particularly about particles and the pollution on particles and its health effects. And so they're just beginning to grapple with some serious pollution problems. So carbon monoxide looks pretty good today. The nitrogen and nitrogen oxide is down around 1 part per billion, and that's very low. And let's see, the other thing, sulfur dioxide, negative 0.2. So what does a negative number mean? Well, it means that the level is so low that all of these instruments have a little bit of noise. And so it's just noise in the instrument. It goes plus and minus maybe 0.02 or 0.03. And that means that we're beyond the detection limit of this instrument. And so you can imagine, like for carbon monoxide, it was 0.35, now it's down to 0.34. And so you can imagine, and it just sits there swinging 0.34 to 0.36. In reality, it's probably just a constant 0.35, but the instrument has a certain amount of slop or play in it. And so when you get down to zero, you can actually get negative numbers. What this is telling me, and as well as looking at the anemometers on the roof, is we're getting wind from the north. And that's a really cool thing about this station, is that when we get winds from the north, I've worked on the north slope of Alaska in Barrow, which is some of the cleanest air on the planet when there's winds from the north. And we match Barrow, Alaska here in the Adirondacks when we get northerly flow, when the wind's coming from the north. And when it's from the southwest, that's when we get pollution events, as they are here. They aren't to the point of health risk, but we can compare what you might see in nature if there was no human intervention with what we do see on the East Coast coming from the Midwest. The bulk of what we do, it's all physical elements of our Earth, but it's all essential in understanding the biology and the changes in biology and ecosystems. You have to understand physically what the environments are that you're in. And so it gets really exciting when you bring the biologists in and they realize that, if there's an excess of nitrogen, it might be fertilizing certain places. And that might be good. Or in the Gulf of Mexico, where these same sorts of measurements are made on the Mississippi River, there's so much fertilizer put on fields in the Midwest that it goes into the Mississippi River, it comes out in the Gulf of Mexico. The plankton bloom to the point where nothing else can live there, and they call it a dead zone. And it's right now the dead zone there is about the size of Connecticut and Rhode Island put together. It's vast. Fish can't live there. It's just particular types of plankton that like these fertilizers. I've been learning a lot, so I've changed gears, and my expertise is in optical properties of snow and optical instruments. I am not a chemist, and I can't really answer chemistry questions, but it turns out that it really has to be a collaborative effort, because the chemists don't spend their time learning about almost all of these instruments work with optics. So they use light to make the measurement. And so as physicists, we can keep all of this stuff running and be sure that it's running well. And then the chemists can use that information to better understand atmospheric chemistry. Yeah, the summit was, so I work for the University of Albany, and within that university there's a Department of Atmospheric Environmental Science, which does geophysics and atmospheric science, but there's a second group called the ASRC, Atmospheric Science Research Center, and the people working there are not generally teaching faculty, they're just scientists. And so I work for them, and right when that was founded, they had this vision of having a place in the Adirondacks that was very remote, where they could study natural atmospheric processes. And so they began to take atmospheric measurements at the summit, I think in the 60s. In 1970, they managed to get the funding to build the structure that's up there. At about the same time, this used to be a ski area that became defunct, and so they got permission from the Department of Environmental Conservation for us to use that and to clear this area and to build this. And I think that all came online in the late 1980s. We have a record of ozone that goes back to 1975, and records of these other gases that go back into the 80s. And so there's a lot of research that can be done looking at how our atmosphere has changed as these trace gases and particulates have changed. And so I think our long-term atmospheric record is one of the important things we share, but we also occasionally you see trends and you can make insight as to what's changing. And one of the things that we just noticed recently is that ozone peaks in the summer in polluted areas, which is most of the places people live, but we're actually seeing in terms of the seasonal peak, but we're seeing that peak shift toward the spring, which is more what you'd expect in a more pristine natural environment. And so that's a little insight that we can see from this data, and it turns out others have seen similar things in Europe. It hasn't been seen in the US, but everywhere else the ozone is actually going up from year to year on average, and ours is going down. So there's things like that that are of interest to the people who study the dynamics of the atmosphere and the motion of the air, and to try to explain these features that we see in our data sets. One of the fun things about being a scientist is you can figure out your own day, and so it often is not the same for any given day. But I do have a weekly routine where I come up and do work here, do the calibrations on Tuesdays, summit on Wednesdays. If things are broken, then I'm off and fixing them, and keeping up with emails seems to be part of life. And then some of the fun stuff, when everything's running well, and this is what I'm in the thick of now, is working on papers and presentations for conferences. But I can kind of juggle that around, and if I feel like taking a mountain bike ride at noon, because that's the warm time of day, I'll do that and then go home at 6. So I kind of make my own schedule. I studied physics, and but I didn't really like working in the lab, and then I stumbled across what's called geophysics, and it's people who study glaciers and climate and the atmosphere and volcanoes and earthquakes and a whole variety of elements of the physical earth on a big scale. And so I spent about 25 years working on polar climate, and it involved many trips to the Arctic and the Antarctic. And if you like to travel and be outside and to get paid pretty well for it, getting a degree and a career in science is a really good way to do that. And there's a lot of opportunity right now.
Whiteface Mountain is not only home to a plethora of recreational opportunities, the mountain is, in fact, home to a great amount of scientific exploration. The kind that is used to tell a story. The story of our atmosphere. The knowledge involving the negative changes in the environment and the necessary steps to prevent it from future harm is reflected from the data collected here and will ultimately inform policymakers. The data gathered for scientific research directly impacts our understanding of the world around us. The data being collected about our atmosphere shows that humans are major contributors to the majority of environmental alteration. Changing human behavior will be an important step to take to stop the harm being inflicted to our environment. It is the idea of changing human behavior that's the most difficult part of the climate change question. Even if the science is undisputed, if there is not an imminent threat to humans or what we depend on, people are reluctant to change their behavior. Our overwhelming dependency on fossil fuels and other integral parts of our lives makes the transition of behaviors incredibly difficult. Purchasing more energy-efficient appliances, cars and trucks, or heating systems that do not rely on fossil fuels cannot happen by the masses without large-scale intervention by the government and industry. no one really knows how to deal with the many arguments to not change our energy behavior that affects climate. Something needs to happen now, as change to our climate skies out of control.